Hey folks, in this video we're going to be talking about nuclear chemistry, or at least the basics of it. It's not that excitingly basic, come on. So I want you to be able to define what nuclear chemistry is and explain how it differs from other chemical reaction types. I'd like you to be able to identify alpha particles, beta particles, and gamma particles, and I'd like you to be able to predict the products for some nuclear chemical reactions. And I'd like you to also be able to explain how half-life affects radioactive chemicals. So talking about nuclear chemistry is studying the properties and reactions of radioactive chemicals. And these are going to be reactions where the nucleus of the atom is involved, not all those electrons, specifically those outer ring electrons, because as we know, those are the dudes who like to react. And so nuclear chemistry comes from the name nucleus because the nucleus is involved. And so unlike most electrons, protons and electrons are the dudes we're going to focus on here, not the electrons. Electrons can step off the stage for at least a minute. So isotopes with unstable nuclei will become stable by emitting radiation. This would be those different types of particles that I mentioned we'll talk about later. Or talk about them now. The alpha particle, which is represented by this Greek symbol alpha, which looks like a little fishy, is a large particle that might be emitted, and it is made of protons and neutrons. The beta particle is basically a high energy electron. I said we wouldn't talk about electrons, but here we are talking about electrons. And it's represented by the Greek symbol beta. These two dudes are cool. And then there's the ferocious gamma ray, represented by the Greek symbol gamma, which basically we can draw with a Y. And that's a very high energy photon. It is not even a piece of matter per se, but it is a high energy photon. Remember, photons aren't matter. They're electromagnetic radiation. And so emitting radiation, when these nuclei do this, this is referred to as decay. So we might say alpha decay for an alpha particle, beta decay for a beta particle, or gamma decay for a gamma ray being shot out of there. Notice it's not called a particle, it's a ray because it is not matter. It's not a particle. Or debatable. Anyway, half-life is an indicator of how stable an isotope is. So the half-life measures the amount of time for half of a sample to decay, and there's more on this in a subsequent video. But it's basically all we're going to say for now. Nuclear decay. When we talk about these alpha particles decaying, an alpha particle or an alpha decay. An alpha particle is made of 2 protons and 2 neutrons. It is basically the same thing as a helium nucleus. And so when we draw a symbol for an alpha particle, it's frequently they just use the symbol, they and we will use the symbol for a helium nucleus or a halide nuclide symbol, ignoring charge. So here's what it looks like as actual chemicals. There's 2 protons and 2 neutrons. Those are the subatomic particles that make this thing up. It does technically have a +2 charge on it, but typically when we're writing out nuclear chemistry reactions, we're going to ignore that. And so here's what we might see in a chemical reaction when we're talking about alpha decay. This helium symbol with the atomic number and the mass number, typical nuclide symbol. And so the alpha particles are the largest and heaviest form of radiation we're going to talk about. And because they're big and heavy, that makes them not very dangerous. I'm going to say not very dangerous because they are still dangerous. But really, because they're so big and heavy, it's really hard for them to get like into your body. We would say that they have low penetration because they can't break through like skin and clothing. Skin and clothing is enough to ward them off. If you get them inside your mouth or your ears or your nose or any other way in, if they are able to enter your body, then they can be dangerous. Alpha decay is, as I've said, the name for a reaction where an alpha particle is released. And because we're releasing 2 protons from a nucleus, that's going to change the atomic number. Remember, atomic number is the same as our number of protons. And so if we change our number of protons, we're going to actually change the element that we're dealing with. And so whenever we do a nuclear chemistry reaction, we have to make sure that we're still paying attention to conservation of matter. So the mass number, if we add that up for all of our reactants, all their mass numbers, that has to be equal to the mass numbers for all of our products added up, because it should be reactants added up to make all of our products added up. We can't change the mass number total from one side to the other. And the same thing goes for atomic number. We can't change that because if we did, that would mean that we're spontaneously creating or destroying particles. And we can't do that. Remember, you're not that blue dude from Watchmen. Anywho, here's an example of an alpha decay reaction. And as you can see, if I add up the values for all of these mass numbers, 239 is going to be equal to 235 plus 4. And we can use this to help us predict products. And we can see when that thing disappears, the same thing is true for our atomic numbers. 94 on the reactant side is going to be equal to the sum of atomic numbers on the product side. So 92 plus 2 is the same as 94. Look at maybe another example. Here's if another example just represented with particles instead of symbols. And so we can see a larger radium nucleus becomes a radon nucleus and emits that alpha particle. And again, the same thing is true. Our mass number on the reactant side is 226, and our total mass numbers on the product side are 222 plus 4. Or 226. Cool beans. Well, let's do some predicting some products for alpha decay reactions. If you know you're looking at an alpha decay reaction, or you're told you're one of these dudes undergoes alpha decay, the first thing we can do is put in our alpha particle, the helium nucleus. I just copied this off the internet, which is why this appeared here and not there. Just bear with me. So if this is our alpha decay, what is the other product going to be? Well, we can just do some basic arithmetic and say, all right, well, it's going to have a mass number of, this side has to be equal to 233. So 233 minus 4 is going to give me a 229. And we can do the same thing for our atomic number. If it's 92, well, the total over here has to be 92. So 90 plus 2 will give us 92. So our dude is going to be mass number 229, atomic number 90, or thorium. Cool beans. Let's go through a few others. Here we can do the same thing. Our mass number should be 145. Our atomic number should be 62. And we can look that up on the periodic table and see that is, where are you, samarium? I never deal with the rare earth metals too much. Thorium, if that undergoes alpha decay, well, that's going to give us an atomic number of 228 and an atomic number of 88 and a mass number of 228 to give us some really cool radon 228. If platinum 175 undergoes alpha decay, blah, 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 you get the picture. This is going to make something with a mass number of 171 and an atomic number of 76. We can look up 76 on the periodic table and see that it's osmium. So this would be an alpha decay of platinum 175 to give us osmium 171. And last, this neptunium can give us some real cool hey, I don't even remember what the name for that guy is off the top of my head. I never deal with rare earth metals. Anyway, let's keep going. The other type of nuclear decay that we're going to talk about and do a lot of symbols for is beta decay. So beta decay, as I said, is a high energy electron being shot out of that nucleus. And it's formed when a neutron kind of breaks apart. And this neutron breaks apart to create a beta particle that shoots out, a proton that stays behind, and a weird thing called an antineutrino that we're not really going to worry about. But I'll put it in there. Here's our symbol for that antineutrino. Antineutrino. Anyway, so we can see a neutron breaks apart to make a beta particle and a proton. And so, yeah, don't worry about the antineutrino. So this can also represent a positron, but I don't even want to talk about that. If you want to get weird and geek out on particle physics on the internet and the YouTubes, I totally recommend it. Basically, though, the real implication here is a neutron becomes a proton that stays behind. So we're going to change our atomic number, and we're going to spit out a beta particle. And so here's a visual representation of that. We see lithium, the mass number stays the same because a proton and neutron have the same mass. So when a neutron becomes a proton, we're not changing the mass, we're just kicking out a little bit of electron. But our atomic number changes, so our element is going to change. Nifty, and there is our fun beta particle. So the beta particle is really small by comparison to that alpha particle. It's an electron compared to those other subatomic particles. And as you may recall, the electrons are very, 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 very small by comparison. So it can penetrate into human cells, and if it does so, it has enough energy to smack into your DNA and potentially alter it, and that's bad. So beta decay, as I've said, our atomic number is going to be increased by 1 because a new proton is being formed. And so the mass number, as I said, is going to be staying the same because one neutron is being destroyed, but a proton, which has about the same mass, is left behind in its wake. So just as before, our total mass numbers and atomic numbers need to be equal on the reactant side and on the product side. So here we have 8. That's going to be equal to 8 plus 0. Cool. We've got 3. 3 is equal to 4 plus a negative 1, or 4 minus 1. Nifty, nifty. Here's another example. We've got some strontium-90 undergoing beta decay to form yttrium-90. The only thing that really changes between those two is the symbol for the element and the atomic number. Here's another example of americanium becoming californium. We do know those guys. And again, the only thing that's really changing is the element. So our atomic number increases by 1 and thus we have to change our symbol. So why don't you pause the video and try and predict the products for these guys? Oh, I already went through that one. Why don't you try and predict the products for the rest of these, assuming that they're beta decay? Pause the video, try it out now. Sick, you tried it out. Well, let's just go through them. Again, in every case, we're going to see that our atomic number increases by 1. So all we need to do is have a periodic table handy to reference our new chemical. I know the bromide's going to be formed from krypton. And technetium, well, that's going to form our friend rubidium. Sorry, not rubidium, ruthenium. You're so much cooler than rubidium. Anyway, let's talk about a little bit more nuclear decay. Gamma rays. These are not as fun to write reactions for. They're the highest form of nuclear radiation, which is cool. It's just a photon, though, a massless particle. And so because of this, we're not going to write out fun reactions for it because we're not going to have changes in masses and dealing with protons. So very unstable nuclei can spit out these gamma rays. And because gamma rays are just photons and have no mass, they're like super, super small with a ton of energy. And they can totally like shoot right through your body. So that's bad. They're very good at causing damage to DNA. So if you're exposed to a lot of gamma rays, you will probably just get a lot of cancer and die as opposed to becoming a Hulk. So during gamma decay, the structure of the nuclei or nucleus is pretty much unchanged. It's just kicking out a little bit of energy. We can imagine it being high energy here and then it spits out an electron, or not an electron, silly wine, Brad. That would be some gamma or some beta decay. It spits out a photon because it's undergoing gamma decay, and then it's not as wild. It's still not stable, probably, but it's a little bit less wild. So we don't really write equations for gamma decay because nothing changes. It's just one element that stays that same element. It just kicks out a photon. So half-life, I mentioned that a little bit before. Well, it's a measurement of the time required for half of the sample to decay. And this can be really, really fast or really, really slow, like it takes billions of years. Every isotope has its own half-life. And most isotopes have to go through multiple phases of decay, spitting out different types of particles before they actually are able to form a stable nucleus. This is a thing called the Decay Series. It's the series of nuclear reactions an unstable isotope has to do before it actually becomes stable and stops spitting out particles. And so because different isotopes decay at different times, they're going to also be producing different types of radiation, not because, but just they decay at different rates and produce different types of radiation. And so this is all going to be summarized in a decay series. But using half-life, we can sort of figure out how long stuff will take to decay. So let's do like an example problem here, and I'll talk through it. Like if we have 100 grams of tritium, how many half-lives, we don't know the half-life here, but how many half-lives will it take before it becomes 25 grams? Well, we do have the half-life. We can look up our friend tritium and see that it's 12.3 years for half of a sample of tritium to decay. So if it takes 12.5 years for half of a sample of tritium to decay, well, that's 12.5 years, and our 100 grams will become 50 grams. And in another 12.5, but it's in another 12.3 years, our 50 grams will decay in half, and we'll have 25 grams. So, as I said, in 12.3 years, half the original sample will be gone, so we'll have 50 grams. In another 12.3 years, another half will be gone, so that 50 becomes now 25. So it's going to take us 24.6 years for this to decay. We'll talk more about half-life problems in a later video. Let's look at this decay series really quickly because it's kind of nifty. This shows that if you have uranium-238, it's going to go through all of these unstable nuclei before it finally becomes that cool guy lead-206 at the bottom, who is actually stable. And if you look through these, some of these decays vary from billions of years to fractions of a second. And what's really kind of cool in here is the radon-22 decay series. You may know that radon is a dangerous gas. Well, that's because radon is a gas, and it has a relatively short half-life. And then after that half-life, it goes through a bunch of stages that kick out a bunch of alpha and beta particles really quickly. So if you breathe in some radon and it does this little decay chain inside your body, it's going to pew, 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 spit out a lot of radioactive particles inside your lungs. And that's bad. Anyway, stay out of the danger zone. Other stuff on nuclear reactions, real quick, is we should talk about fusion. These are two types of reactions I'm going to talk about that are not decay. And fusion is when two nuclei join together or fuse. This occurs inside the sun and stars. And it's nifty because all of the atoms that are anywhere are built from fusion inside of stars, and then when those stars in a supernova, which not all stars do, but if those stars in a supernova, that is how they disperse those atoms throughout the universe, or probably within their own galaxy. So fission, on the other hand, is not when things combine, but when one nuclei breaks apart into two other nuclei. And this is what was used in traditional nuclear weapons, and it often produces a lot of other particles, lots of radioactive particles, which is why radioactive weapons, one of the reasons why radioactive weapons are bad. Anywho, here's an example visually of a fusion reaction. We see two helium nuclei coming together to make a beryllium, smushing together. And here is an example of a fission reaction where we can see this uranium is inspired by this neutron to unstably blow apart into two other guys and release a lot of energy. And one thing I should say before this video concludes is that all of our nuclear reactions are going to be pretty intense in releasing energy. Most nuclear reactions are going to be exothermic. Anywho, that's the end of this video. It's a long one, so I'll just wrap up and say ta-ta and have a great rest of your life.